Yesterday's class was about moving coordinate system, and we continue on the same line. So, what we did in the last class is we considered a situation where there are two coordinate frames. One is stationary, which we labeled as x prime, y prime and z prime, and there is another coordinate system which is moving. We called this x, y and z, and the movement is taking place around an axis which is given by n capped, and the velocity of movement, instantaneous velocity, rotational velocity is omega. So, in this situation we have shown that time derivative with respect to this fixed frame and this moving frame of any arbitrary vector g is related by dg dt fix is equal to dg dt rho plus omega cross g. Now, we proved that assuming that by one particular property of a rotating vector, if this is a fixed direction around which a particular vector is rotating. So, this is one position of the vector. So, essentially the vector whichever is rotating around this particular axis has to stay on this cone, okay, on this surface. Okay, I will just draw it a little bigger for you guys, so that So, let us say this is the direction n capped, and this is one position of that vector, and this is another position of that vector. So, let us call this vector A here and A plus delta A here, as the direction is changing. So, this vector A is not fixed anymore. So, the deviation from this here to here is given by delta A, right. Now, what we did was we took the angular deviation theta, and we have shown that this delta A can be written as, the magnitude of delta A can be written as A delta theta, okay, and the vector direction is on this way. So, that is, if we take the cross product of omega and A, sorry, omega is in this direction, omega is along the direction of n capped, okay. So, if we take the cross product of omega and A, in the limiting case the vector dA will have the same direction. We can also have an alternative proof for it. If you simply join this, and let us call this angle delta theta instead of this angle, it will be, sorry, this will be delta theta, okay. So, it is the same thing essentially, because this and this angles, they has to be equal. It is just the 2D projection of this particular case, okay. So, we can, and if this angle is phi, then this length we can very easily show that this length is A sin phi, and so dA will be A sin phi times delta theta. So, it will be dA will be equal to A sin phi delta theta, right. So, dA dt will be A sin phi d theta dt, which is nothing but omega, because omega is the rate of change of theta, or rate of change of this angle, this particular angle or this particular angle, whichever you want to look at it, okay. And once again, if you want to calculate the, explore the direction of this changing vector, then you can write this as, okay. So, this can be written as A sin phi omega, because d theta dt is nothing but omega, and in vector term dA dt is nothing but a sin phi, sorry, not a sin phi, but a omega n cap cross a. This will give you a sin phi, n capped has a magnitude 1. Okay. So, n capped cross a will give you a sin phi, and this n capped times omega is nothing but omega. So, this will be omega cross a. So, either we can directly take this angle and d theta and compute delta equal to a and delta a and show that dA dt is equal to omega cross a, or what we can do is we can take the 2D projection of this particular problem in this plane or a plane down here as you wish, that is totally up to you, and we can again prove dA dt is equal to omega cross a. Now, the important result is dA dt is now using this important result we can finally conclude that this is the case for any vector g which is moving which is represented either in the fixed coordinate system or in the rotating coordinate system. Now, as this relation is true for any vector g, what we could do is we replaced g with r and we showed that its V0 is equal to V plus omega cross r, right. Now, what is omega cross, what is V0? V0 is the velocity of a moving body which is measured with respect to this fixed frame, and V is the velocity which is measured with respect to this moving coordinate system, rotating coordinate system. So, we can now instead of taking g equivalent to r, we just take it as V0, and using this form of V0 we can write d dt of V plus omega cross r equal to d dt dot V plus omega cross r plus omega cross V plus omega cross r, right. So, this we can write, and simplifying, see actually this side we do not have to do it, sorry, we can just keep this as V0. Okay. So, now this will be nothing but d2 V0 dt2, right, and on the right hand side we have, so this V without a suffix. Okay. So, this is the velocity as which is measured in the rotating coordinate system. So, if we take this time derivative once again, it will be simply d2v dt2, and next term we will have a omega dot cross r plus omega cross r dot plus omega cross v plus omega cross r, right. Now, omega cross r dot, please remember this r dot is once again the velocity which is measured in the rotating coordinate system. Okay. So, r dot is the time derivative which is taken in rotating coordinate system, that is the velocity v in rotating coordinate system. So, we have this term twice. Okay. Now, this term if I multiply this whole thing, sorry, this is not d2 v dt2, it is simply dv dt, sorry. So, if I multiply this whole thing with mass of this particle which is invariant, because mass is a quantity which is invariant under any coordinate transformation. So, well, in the non-relativistic world, in the relativistic world we have a different story altogether, we are not going into that. So, if the mass is constant, so if we multiply this both side of this equation with mass, what we get is a mass term everywhere, here and here, right. Now, look at this term m dv dt, and this is measured with respect to the fixed coordinate system. Now, Newton's law is valid in a inertial frame, which is, in this case, the inertial frame is the fixed coordinate system. The other coordinate system is rotating, so it is not an inertial frame. Now, according to Newton's law, F is equal to m dv dt. Okay. Now, in this case, in the current notation we are using, it will be dv0 dt fix. So, this term on the left hand side gives you the net force which is acting on the particle of mass m. Okay. So, that is the true force, because this particular term, it's once again, this is the acceleration term multiplied by mass in the rotating coordinate system, which has the same dimension of this one, but this is the actual force because this is measured in a inertial frame. Now, if we rearrange this equation from here, if we rearrange this equation, replacing this by f, okay, and keeping this into one side and rest in the other side. So, we can write this as m dv dt is equal to f plus, now it will be twice m into omega cross v. Now, when we change sides, the cross product will also change side. So, it will be twice m v cross omega, right. This will also change sign. So, it will be m r cross omega dot, right, plus, now the last term will be m omega cross r cross omega, right. So, this is the actual force, and all these three additional terms are the fictitious or pseudo forces, which is a result of this rotating coordinate system. Now, please understand this force is measured in the fixed frame, in the inertial frame, and the pseudo forces, they do not exist in the inertial frame. Because right now we have written in this equation in a particular form where we measured the velocity itself in the moving coordinate system, all these additional fictitious force terms, they appear. Now, consider Earth as an example of moving coordinate system, as we discussed in yesterday's class also. What happens? We have, this is our Earth. Let's consider it to be a sphere. Okay. This is the direction of omega being the velocity of rotation for Earth, and so it is rotating in this particular manner, in this particular direction. Now, omega is constant. So, at least for Earth, this term has no meaning, because this is mr cross omega dot. If omega is a constant, then this term will vanish, but these two terms will survive. So, especially when we are writing this equation for Earth, we can get rid of this particular term, but these two terms will still survive. This term is called Coriolis force. I think you are familiar with this, and this Coriolis force causes the monsoon. This Coriolis force causes cyclone to rotate in a particular direction. This Coriolis force causes river to bend in one side of the river bank to go up and other side to go down. And also for this Coriolis force, horizontal cannon shot deviates from its line, vertical falling object deviates from its path. All this happens for this Coriolis force. So, we will discuss that briefly, and this one is the familiar centrifugal force which acts on any object on this planet. Now, because of this particular force, okay, so will go into it in in details. What happens because of this force? This force is actually, if we draw this the components of omega and r carefully, let us say on any object at this particular position, this force will have a direction in this way. Also the magnitude will be very small because it is of the order of omega square. Omega itself is a small number, we will see very soon. This will have a magnitude which is small, but please understand this, although small, it is non-trivial, there is a effect of it. So the acceleration due to gravity, which is g, which is the gravitational pull of earth, is along this particular line. Because of this presence of this force, the acceleration will not be along this particular line, but in a line which is slightly deviated from it. Please understand the magnitude of this force is very small. Okay. So if we draw it at scale, it will be almost non-existent, but because of centrifugal force, our true direction of true gravitation acceleration is not exactly towards the center of earth, but slightly deviated from it. Okay, so we will take it up later on, but right now let us focus on Coriolis force on earth. Okay. So we will first have to define a coordinate system on our planet, and then we will take it up in a more systematic manner. Right. Okay. First of all, what is the magnitude of omega? Omega is the Earth's speed of rotation, and this has a magnitude of 2 pi by, so the complete rotation takes place in 1 day. So the magnitude is 2 pi by 1 day, that is 24 hours, okay, which will be, I will have the number somewhere here, right. So it will be 2 pi by 24 into 3600, and if you calculate this, it will be 7.3 into 10 to the power minus 5 radians, right? Yeah, 7.3 into 10 to the power minus 5 radians. So please keep this number in mind, we will be using it a lot, right? Now let us first start defining a coordinate system, and then we will be discussing Coriolis force. This let us go to this particular point on earth, which is at some latitude, okay, I think this is better, some latitude theta. Okay. So this is the equatorial plane of earth, and we are at this particular point P, which is at a latitude theta on earth's surface. Now what happens is, okay, I think I will just switch to pen and paper. So this is our planet. Again, my drawing is never very good, excuse me for that. Okay. So this is the equatorial plane, and this is a point of our interest. Now where is omega? This is the center, so the axis of rotation is this. So this is again the direction of omega, which is a rotation in this particular direction. Now let us try to define our coordinate systems, which is along the same line which joins this point to the force center. So if I extend this line above the ground, please remember, understand this blue part is inside the ground and this red part is above the ground. So this is my Ez direction. Let us call this coordinate system Ex, Ey and Ez. Now, it is a right handed coordinate system. Now, how do we draw a right handed coordinate system? Typically, this is my x, this is my y, this is my z. Now, try to place this point here and try to align y towards the north pole. If you do that, this is your y, you will see that your x will be somewhere in this direction. Okay, it does not look very, the angles does not look very right, but these angles are all 90 degree. So, this is my x, or rather I will call it Ex here, and this is my Ey. So, this is my Ey direction, this is my Ex direction. Now, try to place this omega vector at this origin, right. So, this is once again your omega vector, and now, okay, where is it? Yeah. Now, this angle is your latitude, which is given by theta. So, this angle once again is theta. So, this angle will be 90 minus theta, right. So, if you recompose this omega vector or the angular velocity vector into this new coordinate system, the components of that will be omega along Ex equal to 0, omega along Ey is equal to, see, it will be 90 minus theta. So, this angle will be theta. So, it will be omega cos theta and omega Ez equal to omega sin theta. Now, if you look into, I mean, if you are studying books by, for example, Goldstein and many other textbooks, where you will see that this component has been resolved, the components of omega has been resolved with respect to the co-latitude, which is this angle. So, instead of having omega cos theta and omega sin theta, they have omega sin theta and omega cos theta here. Okay. So, which is also true, please you have to make sure you understand which angle it has been resolved around, whether it is the latitude or the co-latitude. I prefer latitude because that gives you a straightforward physical picture. Now, so we have omega cos theta and omega sin theta, and if you study these components carefully, see, theta is the latitude. So, if you go to the poles, theta will be equal to 90 degree or either plus 90 degree or minus 90 degree. In both cases, omega Ez will be maximum. So, we have maximum at poles, and if you come to, oh sorry, wrong, it will be minimum at pole, minimum at poles and maximum, just give me a second, yeah, that is true, minimum at pole and maximum at equator. Equator is this plane in the center 0 degree, where theta is equal to 0 degree, right. And this one, this is minimum at equator and max at poles, right. Now, the Coriolis force is given by 2m root over v, 2m times v cross omega, no root over, sorry. Now, if we consider an object which is moving in the horizontal plane of this on this coordinate system. So, this point P is not a fixed point, we can move it anywhere in the on the earth's surface, in the northern hemisphere, southern hemisphere. Okay. So, we essentially we have the same type of component resolved, we can resolve the same components for omega. Now, also please note that omega Ez, this is the component which depends on sin theta. So, as theta is positive in the northern hemisphere and negative in the southern hemisphere, omega Ez changes its sign in different hemisphere, whereas omega Ey, the y component, remains invariant. Does not matter whether you go to northern hemisphere or southern hemisphere, omega Ez remains the same. So, now if we consider the velocity v to be resolved into two components, Vx Ex cap plus Vy Ey cap, then we can compute this to be equal to 2m Ex cap Ey cap Ez cap Vx Vy 0, and this will be 0 omega cos theta omega sin theta, which will be equal to, okay, forget about 2m, it is always there. So, it is a 2m here. So, Ex cap will be Vy omega sin theta, okay, minus 0 plus Ey cap. There is a twice m here outside, so please keep that in mind. Ey will be this minus, so it will be 0 minus Vx omega sin theta plus Ez cap will be equal to okay, so this minus this, so it will be Vx omega cos theta. So, we see that there will be components not only in the xy plane, but also in the z direction. So, that z direction component in z direction eventually means there will be a vertical shift of this this particle of mass m, which moves with this particular velocity. But for now we just neglect this, we just ignore this term, and we try to see what happens, what deviation the particle suffers in the xy plane. Okay. So, the Coriolis force Fc, if we write it once again, we can write this as omega sin theta Vy Ex cap minus Vx Ey cap. Okay. Now, look at this particular vector over here, and so this is a vector here. So, we have this. Now, this vector, if you take the dot product of velocity with this vector Ex cap minus Vx Ey cap, which will be V has to be replaced by Vx Ex cap plus Vy Ey cap, right, dot Vy Ex cap minus Vx Ey cap, you immediately see that this will give you a big 0, right. So, you see, if in the xy plane I am just drawing a trajectory of the particle in x and y plane, if this is the initial direction of velocity v, we get a direction of the force F, we get a particular direction of the force F, which is by this particular dot product, we immediately understand that the deviation is always in a perpendicular direction. So, if we fire a horizontal cannon shot with an initial velocity v in the xy plane, it got deviated by certain amount in the xy plane. Now, try to see in terms of this particular picture. Okay. Let us assume that the cannon shot is fired along Ey. So, initially it has only y component. If only Vy component survives, then in the Coriolis force you see there is always only a Vx component. Okay. So, if we fired the cannon shot along the northern direction, because y represents direction towards north. So, if we fired the cannon shot towards the northern y direction, so it will get a deviation in the x direction. Similarly, if we fire a cannon shot only in the Vx direction, which is the east direction, so please understand that this is north and this is east, this particular direction is east, right. So, if we fire it along the Ex direction, so Vy is equal to 0, then we see the deviation is along EY direction, minus EY direction, minus EY is south. So, that means if we fire it along this direction, the deviation is down south here. So, that is in the northern hemisphere. Now, if we come in the southern hemisphere, what happens is when we change theta to minus theta, this particular term changes direction. So, in the southern hemisphere, what happens is if we fire a horizontal, so in this is the case of northern hemisphere. So, we get a deviation towards right hand direction in the northern hemisphere. Okay. Now, what happens in southern hemisphere? In southern hemisphere, because of this particular term, it will change its sign. So, if we start with a Vx, okay, so we will get a minus Vy, but there is a negative sign coming from this one also. Okay. So, effectively we will get a deviation in the y direction. So, in southern hemisphere, if you start along the east direction, you get a deviation in the north direction. If you start along the y direction or north direction, then you get a deviation in the southern direction. So, if you are firing in a general direction this in the southern hemisphere, then your deviation will be in the left hand side. So, essentially you can think of it this way: your velocity vector, if you are standing on the northern hemisphere, your velocity vector and your omega is towards, general direction of omega is upwards. So, your v cross omega will be a vector which will be going to the right of your velocity vector. Whereas, if you are standing somewhere in the southern hemisphere, omega is actually going inside the ground here. So, your v cross omega will be a vector which will take you, which will direct towards the left of your original velocity direction. Okay. So, we will continue from here in the next class. Right now, let us stop. Thank you.